Welcome, everyone. Today we are exploring the first part of Chapter 10, focusing on understanding multiple regression analysis. Throughout our course, we've investigated complex social phenomena such as factors influencing college student depression. While simple bivariate relationships give us an initial glance, real-life human behavior is shaped by interconnected influences like stress, self-esteem, and financial concerns. In this presentation, we will examine why social scientists rely on multiple linear regression to isolate unique relationships, manage confounding variables, and implement statistical controls when true experimental control isn't feasible. Let's begin by considering a practical social thought experiment. Consider two friends with nearly identical lifestyles, sleep patterns, financial status, and social circles, except one has significantly higher self-esteem. Standard intuition suggests the friend with lower self-esteem is more vulnerable to depression. However, in observational social science, individuals differ across countless dimensions simultaneously. Unlike laboratory scientists who isolate variables through strict experimental controls, sociologists and criminologists study people in natural social environments. Consequently, when low self-esteem co-occurs with financial strain or high stress, we need statistical techniques to determine whether self-esteem independently influences depression after accounting for these other co-occurring background factors. This table displays the bivariate correlation matrix examining student depression. At first glance, self-esteem shows the strongest inverse correlation with depression, followed closely by stress and financial stress. It might be tempting to conclude that raising self-esteem is a simple singular solution. However, correlation matrices reveal that independent variables are also correlated with each other. For instance, stress and self-esteem are highly related. Bivariate correlations cannot tell us which relationships persist when all factors are considered simultaneously, nor whether one variable masks or explains another. Regression analysis is an essential tool for evaluating causality, though it cannot prove causation on its own. Establishing a plausible causal relationship requires three core criteria, according to Agresti and Finlay: statistical association, proper temporal ordering, and the elimination of alternative explanations. Social scientists rely on multiple regression primarily to address the third criterion. By simultaneously controlling for demographic background, academic stress, sleep quality, and social support, regression allows researchers to test whether a specific predictor retains its effect or if the relationship is merely an artifact of an unmeasured confounding variable. Ordinary least squares, or OLS regression, is the most widely utilized regression technique in social research. Visually, simple linear regression fits a single line through data points to minimize the sum of squared vertical distances between observed sample values and predicted values. Multiple linear regression extends this geometric concept into multiple dimensions, fitting a multivariable model. Instead of looking at stress or self-esteem separately, OLS allows researchers to evaluate how each predictor uniquely impacts depression while holding all other model variables constant. It provides clear metrics on individual predictor contributions as well as overall explanatory power. The foundational multiple regression equation is expressed in this equation. Here, y represents our predicted dependent variable, such as the student's depression score. The intercept is, or a, reflects the baseline starting value when all predictors equal 0. Each coefficient b measures the expected change in y for a one-unit change in that specific x, holding all other variables constant. The error term accounts for unmeasured individual variation. Additionally, the model yields r squared, representing the total proportion of variance in depression explained collectively by our predictors. We will review this equation in more detail in the next course module. In clinical laboratory experiments, researchers isolate cause and effect by physically controlling the environment or using random assignment to balance unmeasured variables across treatment groups. For instance, in a clinical trial, subjects might be given identical diets so nutrition cannot confound drug efficacy. However, observational researchers cannot randomly assign individuals to family backgrounds, income levels, or traumatic events. Statistical control bridges this gap by measuring these background characteristics and entering them into the regression equation as control variables. This enables researchers to mathematically hold factors like stress or financial strain constant when evaluating self-esteem. One of the biggest challenges in social science research is identifying spurious relationships. Sometimes two variables appear to be related, but after closer examination, we discover that a third variable explains the relationship. A classic example is the relationship between height and math ability. If we looked only at the data, we might conclude that taller people are better at math. Maybe taller people have larger brains that help them solve math problems. Fortunately, that is not the explanation. The real answer is a third variable, age. As children grow older, they become taller. At the same time, they spend more years in school learning mathematics. As a result, older children tend to be both taller and better at math. Height itself does not improve mathematical ability. Instead, age influences both height and math achievement, creating the appearance of a relationship between the two. Constructing an effective regression model requires thoughtful theoretical foundation long before executing statistical software. Variables should never be added arbitrarily or solely based on correlation strength. Researchers must rely on established sociological theories and empirical literature to select relevant predictors across multiple domains, such as demographic characteristics, family background, financial stress, sleep quality, and self-esteem. Omitting crucial variables can severely bias the estimated coefficients of included variables, while including irrelevant variables reduces model precision. Sound research design ensures every variable serves a clear theoretical purpose in explaining the outcome. In conclusion, this first part of Chapter 10 highlights why multiple regression is indispensable in observational social science. It empowers researchers to move beyond simplistic bivariate correlations, isolate unique relationships while holding other factors constant, and guard against spurious conclusions. By combining theoretical insight with statistical control, regression builds realistic models of complex social phenomena like student depression. In Part 2, we will put these concepts into practice by learning how to read standard statistical software regression outputs, interpret unstandardized and standardized coefficients, assess statistical significance, and translate statistical findings into meaningful social research insights.